Good morning, folks. I'm Dave Kehlet. I have two topics I'm going to cover today. Really, again, on this theme of chiplets and extending Moore's law. I'm going to talk about the advanced interface bus, which is a good one to have coming right after Mark's presentation. And another topic about a protocol, link layer protocol work group. But I'm going to give a report out of what the ODSA subgroup is doing in that area. The problem with quoting Gordon Moore is that everyone quotes Gordon Moore. So you folks saw this this quote earlier from DJ, but it's a really interesting one because he did anticipate that in the same paper that he established Moore's law about the doubling of transistors in a given area every year, he also said that it may prove to be more economical to build large systems out of smaller functions, which are separately packaged and interconnected. And so that's kind of the concept of chiplets. So just to give an idea how this works, and I thought this would be really appropriate for a group like OCP. You know, walking outside and taking a look at the exhibits out there, it's about big iron and giant systems, and we're down here at kind of the transistor and electrical level. That the idea is that with a library of chiplets that might span multiple semiconductor processes, might span multiple functions, SoCs, FPGAs, that you could construct a device, a multi-chip package that contained multiple elements here that were optimized for best in class, that you could select among these, that you didn't have to build it all monolithically like is often done today. So you could combine things and create a system. This is a really popular idea particularly with some of the customers that I work with in the US government space, where they might build 10,000, 100,000 of these, and therefore developing a monolithic device in those cases is a little bit of a challenge. And if they could pick from a library here, they could see a way to maintain competitiveness and get all the advantages of the commercial volume. So I started thinking, since Gordon Moore back in 1965, why are chiplets interesting? And there's some really good reasons. One of them that's right in front of us here is this heterogeneous integration. You can mix processes. You can take something that works really well for analog D to A and then mix it with an advanced digital logic process like we have for our CPUs and FPGAs at Intel, and put those two things together. They don't all have to be on the same process. This one's got more important over time, as is the next one. It's taking longer and longer to develop a very complex system. They are more complicated. They take more engineer years to put them together. You don't need to port everything to a new node if you can reuse pieces that you have from the library. And there's another one here about advanced packaging technologies that over the last several years, some new technologies have been introduced that allow a different design style than we've been able to do traditionally with our typical organic substrate packages. So to illustrate this, if you take a standard flip chip packaging technology here, you get about 28 to 34 IOs per millimeter per layer on that. And with advanced packaging technologies such as Intel's EMIB, such as a silicon interposer technology like TSMC CoWoS, you get about a 7 to 8x number of IOs per millimeter per layer. So that's what you get out of the advanced packaging technology, and it allows for different design style if you do this. There are also some interesting other technologies. There was a semicon packaging conference this summer here. There are a lot of folks looking into what they call fan-out technologies, where you might get something that approaches the silicon technologies at a reduced cost. So there's a lot of interesting work here, and the packaging has shown over time that these technologies get cheaper as they mature. So, talking about the design style, the question is that if wires were free, wires on your packaging were free, how would you design things? So I took a look at, we have 500 wires per millimeter in the EMIB that we use on our Stratix 10 FPGA and our new Agilex FPGA. Let's suppose that a typical interposer costs you this tiny fraction per wire. The conclusion from this is that you should spend very little at the end of each wire because you're not necessarily I/O limited. You might be bump limited, but they might be matched to the circuit as well. So you don't want to have a huge, gigantic circuit at the end of each one of these wires. And furthermore, most folks, when they're designing their chips, are not designing the interior of their chips to go 16 gigabits per second. You're not designing your module-to-module on-die interfaces to go 16 gigabits per second. So more gigabits per wire is not necessarily better, because really how you would do it all on die, you might run it a gigabit, you might run it 2 or 4 gigabits if you're a CPU even. So that's something to consider, that the more gigabits per second isn't necessarily better, because it does cost in latency, does cost in serialization. Now, I tried to pick what's the complete opposite end of the spectrum, the most ridiculous example of expensive wires I could come up with. And I found one out there, and it's this faster trans-Pacific cable. Laid in 2016, it has 12 wires that go across from North America over to Japan, and the cable costs $300 million. So that's $25 million per wire. So 5 trillion times more per wire than we have on EMIB. Now, this is a disclaimer back to my legal slide about performance claims made by Intel. But really the conclusion here is that in this situation, you should spend everything you can at the end of the wire because your wire is so expensive. And they have gigantic buildings of terminal apparatus with huge, sophisticated cooling, power, and encoding to get as much data as they can over each individual wire. So I have a chiplet flow chart here. If you support chiplets, you go down the bottom, and if not, go home. I don't really mean go home, but the whole conversation about chiplets, I just kind of touched on it here. A person from Intel, Ramuni Nagasetti, has done some really interesting articles and interviews about the economics behind chiplets, why this makes sense compared to development cost. And so that's a much longer discussion about really do chiplets make economic sense. Here I really wanted to talk about the chiplet interconnect technology. So the next decision that you have is advanced packaging. And this is an interesting one because it has to do with really what kind of interconnect are you going to pick, what kind of circuitry you're going to put behind the interconnect here. Now, if you don't want to use advanced packaging, back to that slide that showed the wiring density of standard flip chip technology, you must serialize. You have no choice, because compared to the on-die wiring that you have, and I don't necessarily mean 112 gigabits per second, it could be the 16 gigabits per second that Mark talked about here, but you have to, in some form or another, serialize faster than you are actually operating inside your SoC. If you do use advanced packaging, you have an opportunity to use wide parallel. And I mean really wide parallel. This could be 1,000 wires going across each direction. So we had some good conversations between the principals of ODSA, and the conclusion was, I think to the group's credit, that the tent at ODSA is big enough to include more than one standard. And I wanted to speak a little bit about the one I work with a lot, which is Advanced Interface Bus, and it is a clock-forwarded parallel data transfer, just like DRAM. You've got a bus of data and a clock, and the other direction you've got a bus of data and a clock. It is really intended for advanced packaging technology. It's where it shines. If you're using standard packaging, organic packaging technology, this might not be the best technology choice for you. It is the PHY. We have a whole other set of discussions about what happens above the PHY here that I will give the readout on the second half of this presentation. AIB is the PHY level, and you build protocols on top of this. Now, here's the interesting thing about an AIB-based chiplet ecosystem. We have 3 chips in production right now with Stratix 10. This is our L-tile, H-tile, and E-tile. These are all SerDes and Ethernet SerDes, PCI Express SerDes chiplets. We announced with our new Agilex FPGA a whole nother set of chiplets, 112 gig SerDes, PCI Express Gen 4 that includes Intel's proprietary UPI protocol on top of that. We have R-Tile that has Gen 5 with CXL. And even the opportunity, you see the other chiplet in the lower right there, that it could be composed with your own IP. We also have participation from the industry. Folks that were at the panel yesterday, I called out Scott Powell from Jarrett, who's in the audience here, is building an AIB chiplet for a high-performance ADC that's really useful for wireless applications. IR Labs announced at Hot Chips a photonics chiplet using AIB. Others coming soon. On Monday this week, eSilicon announced their HBI Plus, which has AIB support as an IP offering that they provide. So we also have others in the works here as well. Last fall, we released the specification for AIB, and this is the full set of electrical specs, testing requirements. This is available at our GitHub site. You can download, take a look at the specification here. Really, almost more interesting, in February this year, we released AIB as open source. And so this is RTL code, it's netless, it uses a generic cell library. It's available at the same GitHub site. This is one of a single-digit number of open source Intel projects that's out on GitHub. There's hundreds of Intel open source software projects, but the open source hardware movement is really becoming attractive. Now, our reason for doing this is we are not trying to monetize the AIB interface. Our interest is getting other silicon that interoperates with Intel silicon that can provide a better solution to the customer. The purpose of releasing this open source is increase access to this technology and reduce the upfront development cost. Just talking about where's AIB going in the future. Right now we are in production with 55 micron microbump spacing. So this is one of those interesting parameters because this really is correlated to how much silicon area can you spend on what's underneath each bump. The next click down on this has this nice geometric property I illustrate in the lower right here is if you get down to 35 micron, all of a sudden you can collapse the columns of bumps together, and then you still have straight line interconnect between two die, and yet you have a much denser array on the right side than on the left side. So it's really kind of interesting. So if you go higher than this, it's kind of a square root of 2 property here. That if you go to 45 micron, you don't achieve this, so it's really kind of not quite a big enough step. If you get to 35 micron, you get this geometric property here where you can collapse the columns together. So this is how we're going to achieve compatibility between these two bump pitches. The I/O voltage, lower voltage, you have lower energy per bit. Compatibility with our existing portfolio of chiplets is extremely important. We can't let that go. We have hundreds of millions of dollars investment in those chiplets. So this is one of those things where we would have to create dual mode, where you either operate in 0.7, 0.9 volt mode, or you operate in a 0.4, 0.5 volt mode. Now, on the line rate, there are some applications. So these very high bandwidth direct RF sampling ADCs are still pushing the amount of bandwidth going across one of these interfaces here, more than we can handle at this point here. So there is an interest in doubling the data rate. This is that serialization question I was talking about earlier. You have to be really careful about not adding any latency when you do this. Now, so short of actually proclaiming a roadmap, these are all the technologies that would go into a next step forward with AIB. So you can see the microbump spacing, I/O voltage, line rate, that would lead to a new generation. And just getting back to it, the compatibility is essential, that we can't let go of that portfolio of chiplets that we've already developed. So that's everything I had on chiplets and AIB.
The one stuff on GitHub is on Apache 2 license.
Yes. We looked at a lot of different licensing schemes. Intel has done a lot of them. GPL v3, we've looked at BSDL patent, BSD patent, licensing. And in the end, we adopted Apache 2.0 because it was adequate for what we needed. It granted a patent license to anybody who used this. And our customer strongly suggested, please use Apache 2.0 because he's creating a whole set of hardware, open source hardware that uses Apache 2.0. And it's just more convenient to not have to mix licenses that way. So that's what we did. We released all our stuff under Apache 2.0. And this, as you can imagine, with an army of Intel lawyers all scrutinizing this, went through a lot of review on this, and it was, it concluded this was really good protection for Intel and offered a lot of capability to the users. Yes?
If I don't mean this to be a gotcha question. It's a follow-up to this. In your release to the spec, oftentimes in this community, specs with implementation details are especially helpful. The closer you can get to things that look like build instructions, design it. So somebody could pick this up and actually do it in some other facility.
Mm-hmm.
Or something like that. It doesn't matter right up front, but it really matters down the road. Can you talk about attitude on licensing towards that kind of information?
None of this that we intend to retain. There's no proprietary advantage that we're trying to hold with this. We have the bump out for AIB is in the spec there, so exactly how to position this, the eye diagram for the electrical specs on this. In that same folder there's an application note, and it's not an official Intel application note, but it's one that we wrote up to say, if you want to talk to a Stratix 10 FPGA or an Agilix FPGA with a chiplet, here's how you do it. Because you take the interface and there's a few other things that you need to do kind of above the specification to interoperate. So that's all out there. So that's our intent, is to enable somebody who actually wants to build this to make it as easy as possible. I mentioned eSilicon is offering IP based on this. We're working on some really interesting physical design generation technology that could potentially say, import your PDK here, run this script. Now you've generated in your process technology an AIB interface. So that's kind of the theory, if we get there, that could really reduce the expense of building a PHY. If you want to talk to Synopsys and you want to get a PCI Express PHY and controller, it's really expensive. And if you only have 10,000, 100,000 units, you're going to spread this over like some of those US government customers do. That's almost prohibitive to pay that kind of licensing fee. So that's kind of some of the directions we're going to enable folks. Steve, welcome.
Sorry, no, I just was pointing it out there. So.
Great. Yes?
On the actual embedding of the AIB chiplets into an organic substrate, is that area protected by Intel patents? PHYs has the capability and technology to do so.
Okay, so the AIB itself is really substrate agnostic. It doesn't say you must use this. There isn't a channel spec. There's an eye diagram that you need to meet, which means you need to do a little analysis on your packaging technology. At Intel, we have those items in production, use Intel EMIB. We are seriously studying how to implement AIB, FPGAs, and chiplets on top of a silicon interposer technology. And so that's kind of one of the areas that I think Bobby mentioned with the discussion we're going to have on packaging is really how do you get this advanced packaging a little more generally available?
That's my question.
Yeah,
How do you get more available coverage without any intellectual property?
I think the way to do this is, there's multiple people who have the technology to do this. Global Foundries has the technology, TSMC has it, Intel has it. There are other people who independently who have interposer technology. It's not a catalog item at this point. So that's kind of one of the technology areas to push on is really, and maybe the fan out technology will help make this a little more broadly available.
I'm just saying it's at 55 micron bump pitch, it's probably doable with fan out technology already. So just add that to the list of already supported.
Okay, so now I want to give a readout about the die-to-die protocol working group that we have within ODSA. Large list of contributors, collaborators here across many different companies. So it's really kind of a really good input. And I think this one here, I'm very optimistic that we can achieve a small set of protocols that are useful and adopted. Probably a little less contentious than the PHY discussion. Really interesting at the ODSA workshop just earlier here, I heard from both IBM had the same concept of there's two things that are kind of converging into this chiplet world. It's you have the package level integration, things that are currently cards, PCI cards, and you have the die disaggregation on the right side. And these are both two major use cases that are driving chiplets and integration. I heard the same thing from IBM. I heard the same thing from the gentleman from Xilinx. So this kind of seems to be the same, a good consensus on these broad use cases. Now, protocols serve applications, not the other way around. And so that's really what you have to deal with here is that given these use cases here, they're going to drive what sort of protocols fit well to those use cases. Okay, so I'll kind of zoom in on I got a little picture of the model up there. On the package level integration, these are commonly cases that are attached to a CPU. So you can imagine, there's an Intel accelerator card that we sell attached to Intel Xeon. Right now they're PCI Express boards. People use these things want to have a coherent memory model. I think we heard about what's easier to use and what's harder to use. This is definitely something that's easier to use from a programmer, both somebody who's programming the FPGA or whatever SoC it is on the accelerator, and for somebody programming a CPU. Some examples of protocols that one might use here. There's CXL, C6, and OpenCAPI. Now these already have consortia in place for determining what those protocols are. We don't need to do this. We need to figure out how to run those on a die-to-die interface that might not be a PCI Express SerDes. Now on the right side here, the SoC die disaggregation. These are currently on-die module-to-module interfaces. ASIC developers like AXI-style lightweight protocols for communicating from module to module. Some examples here I picked out. It's simply examples. It's not a list of what this group has selected. Is AXI streaming, and AXI for, or we call it memory mapped, is another one that's really useful in this space of ASIC module-to-module connections. Now, so I want to zoom in on the left side here, the package level integration. We have Bobby's famous chart here of the different stack on useful for chiplets. And now across here, Boppy and company anticipated last fall that there would be this pipe interface might be a good cut point here where you could above it have protocols and below this have an adapter that would map from the pipe spec down to your individual PHY. And so that's what we would do with these protocols that have a specified pipe interface and that have consortium already and working groups already defining them. This is the point at which they would interface into a chiplet. Now to just take a little closer look at what is this pipe interface. So I grabbed this from the pipe spec. And you can see it's a parallel interface. It's got transmit data going one direction, a parallel interface to receive data going the other direction. It's got some control signals. Now, so the task here is your PHY may not natively speak pipe. So you create an adapter here. And that would match the pipe spec at the top level. And the adapter converts that into your native PHY interface. It may have to do a bus width conversion. It may have to do some other things if your link bring up protocol is a little different than the pipe spec anticipated. We kind of thought that the PHY provider would be the one likely to create the pipe adapter code. It kind of makes the most sense that, that you build your PHY, that you create the adapter to meet up to the standard level here. And the upper stack from pipe up above can be used as is. Now, there was some interesting discussion here about there might be some points in here a little higher than this real kind of PHY interface pipe level. There might be interesting points to intercept. Now, that's going to take these folks here to officially support some other entry point. And it might be something that allows DisplayPort, USB, PCI Express, CXL, these other ones here to join in and be muxed in automatically. So there might be some other spot here that could open up. But right now, it's at this pipe level. Okay, now going over to the right side of the picture here. This is this SoC die disaggregation case. The challenge here is to say, fine, we're going to have this link layer, whatever it is. What is the boundary between that and the rest of the chiplet? So how does your chiplet talk to the link layer? How does it talk to the PHY, and so on? The group has a strong preference towards using existing protocols. We don't want to create something new. I think that we absolutely can achieve this. Again, some examples here that are being thought of, AXI, ACE, CXS, AXI streaming. The group has come up with some evaluation criteria, a big spreadsheet of protocols across the x-axis and down in the y-axis are the evaluation criteria. The things that are being considered are things like functional requirements. What does the protocol provide for you? Does it provide ordering, virtual channels? Does it provide error correction detection? Performance is extremely important, so throughput, efficiency, latency are criteria that we're taking a look at. And implementation complexity is another interesting one. Does the protocol provide, how does it do flow control? Does it provide for retry? Does it provide error detection? And adoptability of are people using this protocol right now is an important factor. So that would kind of guide us towards picking something that people would actually already want to use. Now, just to give some insight into the complexity here, I pulled up a couple cases that I'm familiar with. Let's suppose you have this high-performance ADC DAC chiplet here, and you want to talk to it. Now, your ideal protocol characteristics here is that your transfer rate between these two chips is linked to the sample rate, meaning it's probably divided down. If you're sampling at 64 gigabits per gigasamples per second, it's divided down to some level, but it's linked. What you get out of that is no gearboxing. You don't have to do some weird ratio of bus width or frequencies to get there. It's a big win. We've used this forever in SerDes. Data arrives every clock. You're getting a sample every clock or set of samples every clock. You don't need to say a data valid. That's kind of the interesting thing here is data is always valid. You want low latency. There's some applications where you want to take what you're sampling, operate on it very quickly, and send something back out the other side. You can think of electronic warfare as one of these cases where you might want to do this. And you want some simple convention on where do samples live within the unit of transfer. So that's kind of one use case. Now there's another one off to the right which has a different set of ideal protocol characteristics. So imagine your chiplet had a memory controller and it talked to some kind of DRAM or memory out there. If you go buy a commercial memory controller right now, typically they use AXI 4 to talk to a Synopsys controller or from somebody else. Now it just happens that this controller is off on another die. You still in your SoC would like to talk AXI 4. Now AXI 4 has 5 channels. It's got a read address, read data, write address, write data, write response. So you have these 5 channels. Pretty much all the PHYs people are talking about have 2 channels. So now I have to get these 5 channels multiplexed onto these 2 channels efficiently. And naturally, in a memory system, you want low latency. And a different characteristic is you'd really like this memory controller to operate at the memory speed as fast as absolutely possible, even if you're not operating at that speed inside your SoC. So it could be asynchronous to the transfer clock. What I conclude out of this is that a single link layer even for this die disaggregation, is not going to serve it well if you only use one. There's probably going to be more than one just to span these kind of two use cases. Okay, so kind of step back up to the top here, our big picture of these two major use cases on package level integration. The pipe interface gives us this low-level interface that can support multiple existing protocols. With pipe, we get all these different protocols that do support a pipe level PHY. On the SoC disaggregation, the right side of the chart there's a lot of innovation happening at the PHY. You know, we've heard about this today. And there are applications where you really want near monolithic performance. These are things that were formerly, you would build them as a monolithic die if you could. It just doesn't make sense given the process optimizations. But you want near monolithic performance, things low latency, high bandwidth, low power. So I think what's going to come out of this is not a single protocol, but we're going to get a very, very small number that are useful for different cases. And that's not all that different than we have right now. You know, for networking cases, you need Ethernet. For CPU cases, you need PCI Express. And you just have to deal with that because that's really matches the use cases. Okay, so just to wrap this up, to make my own version of this chart here, you know, how would you put this all in one? You get your package level integration protocols that incorporate a CPU, common pipe interface. You get your SoC disaggregation protocols. There might be more than one here. You get a link adapter, which maps to the PHY. And these link adapters might have different features, like that memory controller example I mentioned, or the streaming ADC high performance ADC DAC case that I mentioned. So I want to wrap up with a quote from our friend Boppy here, because that kind of helps ground what are we trying to do here with the goal of the organization. And again, it's open interfaces so that chiplets from multiple vendors can interoperate and be assembled into useful products. So the group here is tackling the protocols. This is work in progress right now. If you want to contribute, contact me, contact Boppy. We'd love to work with you. Any more questions?
Dave, I just have one. The process of going through this and the pitch you're making for support for multiple protocols and so forth, I haven't been sitting in a lot of the dialogue watching this, and I'm just wondering, do you get resistance to this concept from anybody that you're working with here?
Interestingly enough, yes. One of my customers said, can't you just pick one? It's complicated to have more than one. The problem is once you get into it, you realize you end up with something suboptimal and you kind of lose all the advantages that the effort you're spending to have this high performance interface. If you don't have an optimized protocol for it, you lose that advantage. And so you end up, regardless, you end up having to specialize. And I think the number can be brought way down. We're talking a small single digit number. So that's one kind of interesting resistance is the concept of more than one is perhaps disappointing to customers who would like a single one. It would just be cleaner and easier to deal with if you could get there. Within the working group itself, I think there's a lot of normalizing. There is not consensus on here's the ones we're actually going to say, you should use these. This works according to the committee. We think these are good. We're not there yet. I do think we'll get there. I think a lot of it is people have to kind of understand each other's viewpoint. Being from the silicon side looking upwards, I have a different viewpoint than people who are from the CPU side looking downward. So there's some kind of normalizing that's happening there.
Thank you.
Yeah, thanks. I'm very optimistic about this Sinclair. I think we'll come up with a very small number who say, these work well, please use these. Where I come from, we haven't until the last few years adopted AXI. We had our own Avalon, Altera-based protocols here, so this is a change for us. I don't have these already done, ready to go. But I think it's something doable over time. We did that with our HBM2 controller. We used an AXI interface instead of a legacy Altera interface when we built that and released that a couple years ago.
Thank you.
Okay, thanks everyone. Great seeing you out here.